Hello, thank you so much, Puppy. My name is Erika. Hi, guys. I'm from Mexico, and also a Judah STEM Summit design team member. So I have enjoyed the summit so far so much. It's just day one, and I have learned a lot. Like all the speakers have been amazing. All the attendees are like with their comments like my mind is blown literally. So thank you so much for staying here. So remember to share your highlights on social media using the hashtag UDSTEM Summit and tag in at UDSTEM 2030, please. And so, yeah, our next professor of bioengineering at Northeastern University, where she uses computer simulations to obtain a better understanding of the chemical interactions that occur at the air water interface inside the lungs. Mona's goal is to use this research to engineer better treatments and methods of drug delivery. Mona was always interested in science and says, the goal of my academic career is to carve a path for future blind scientists so that the unique skills and perspectives of the blind community are embraced by the scientific world. Thank you so much. This is going to be a pre-recorded talk, so let's hear it.
Hello, everyone. My name is Mona Mikara, and I'm a professor of bioengineering at Northeastern University. Now, I also happen to be blind. And so one of the things that I want to talk to you today about is kind of my journey of science and how I ended up where I am. Ever since I was a child, I've always been interested in science. I always was curious about how the world works. I was a PBS kid. I watched Magic School Bus, Bill Nye the Science Guy. I was very intrigued about how things came together and how the world around me worked. And then when I was 7 years old, that's when I got the news that I was diagnosed with macular degeneration and Cone-rod dystrophy. Now, as a child, I didn't really know what that meant. But for everybody around me, it seemed like there was, things shifted. My potential to be a scientist was changed. But I didn't want to ever internalize that. So I continued kind of pursuing my passion. I'm skipping over a lot of detail, but I want to get to the point where I decided in undergrad to be a chemist. And this was around junior year of college. And I had already been doing research in the summers from every summer since my first year of undergrad. So every summer I got an NSF REU. It's called the National Science Foundation Research Experience for undergrads, in which they fund you for the summer and you work on some really cool project. So for me, what happened is I had a friend who had really encouraged me to do that my first year of undergrad. Her name was Shazia Ali, and she basically helped me apply. And that's when I was first exposed to doing computational simulations or computer simulations to studying something chemical. And that was, my first project was in carbon nanotubes. So that summer, I just studied carbon nanotubes. I ran DFT calculations, or basically quantum calculations to obtain the energy, looked at different chiralities of carbon nanotubes. And the world of computational chemistry was opened up to me. And that continued for every summer until I actually landed a full-time kind of, like not full-time, but like a gig during the academic year where I was working with Professor Mala Radhakrishnan, where I was exposed to studying HIV non-nucleoside reverse transcriptase inhibitors computationally. And this is where I basically ran simulations to try to understand how this particular drug interacts with transcriptase and how changing the charges on it might help with inhibiting or not. And so I was like in awe of all the different possibilities that computational chemistry can do. And I had realized that this is something that has a lot of potential. Of course, other people had realized it too, but I loved it on top of it. So then I realized that I wanted to go to graduate school and do something more on the medical end of things, like studying proteins. There's a whole area of computational chemistry where people use for drug design. So pharmaceutical companies will hire computational chemists to be able to do a lot of the predictive work in the beginning, because what you can do is save a lot of money. So imagine if you're trying to design a drug. In the past, before we're using computers, people would try out different things in the lab, they'd just experiment. All of that is materials and it costs money and time. But now imagine that we can now, using existing, obviously, laws of nature or the chemical laws, you can model your system on a computer and predict what would and would not work in advance. So that really helped the pharmaceutical company and companies that still do to be able to do a lot of the R&D or research and development on lower cost. So that's when I decided to go to grad school. I studied a enzyme in graduate school, H. pylori urease, where I learned that inhibiting it or stopping its function would help with a very common infection that happens in the stomach. So that was really cool that I was able to do simulations. We found out that like compounds found in green tea really help with inhibition. We were able to test that out experimentally, like send it off to other people. So usually as a computationalist, like we do a lot of the legwork and then we can just tell the experimentalists like test this out. And so that's what I did as a graduate student. I then moved on to study surfactants as a postdoc, which is a type of substance or material that is hydrophilic on one end and hydrophobic, which means it likes oil on one end and water on the other. And that's where I kind of was exposed to more material science. And then for where I am now, I realized that I wanted to do something that kind of combined both areas. And I realized that there were natural substances in our body that have both proteins and surfactants, and that is pulmonary surfactant, which is a substance found at the air-water interface in the lungs. As you might know, this has a huge relevance in today's world due to the pandemic, and that's what I computationally study now. So now I basically sit down and try to understand, how do these proteins interact with one another? How does the surfactant substance change due to pressure, temperature, all of that, because all of this has relevance in us being able to cure certain lung diseases. And so that's what I work on now. And computation, like just computer simulations, have so much potential. I mean, I skipped over the different methods that I do. I do molecular dynamics and Monte Carlo simulations. And Monte Carlo simulations, which are probability based, can span from applying them to chemistry to all the way to the stock market, to the weather, to even how you draw your cartoons. It is like I'm barely touching the surface of computer simulations. So I hope with that, you guys can check out my website, monamacar.com, or my research website. That's combinelab.com, COMBINE lab.com. Combine stands for computational modeling for biointerface engineering, where you can see what kind of research we do. Computer simulations are extremely useful and helpful, and they are part of the future for sure. So if you want to learn more, definitely check out my websites and feel free to reach me. There's a way to contact me on either of those websites. And thank you for listening.
That was such an inspiring talk. I was amazed by all the things that she's done. I think Professor Mona, I can see how you're a great scientist and a great engineering. It's just how she went from being a chemist to computation analysis and then HIV and then lungs. So it seems like you know what you're doing and it's amazing. Like I love how to like you can use proteins and drugs and do like a lot of things with such little things, literally. But thank you so much, Professor Mana, for that talk. I appreciate it, and I know that our attendees also appreciate it.